Cool. Okay. Hi, everyone. So maybe a little poll first. Who's familiar with topology? Maybe raise your hand. Okay. I'll just go off the stage then. And no, I think it's about half, so that's right. Anyway, so this is a very just short part before I guess Maurice talks about manifolds. And so yeah, let's just get started. So this is some stuff that will also show up in my part later this week. And I guess it's mostly like just the basics and some keywords just to make sure we're all on the same page because they show up often. All right. Oh, actually, I can't use. OK. Right. So we start with metric spaces, which is, judging by the raise of hands, many of you will already be familiar with this. But essentially, it's just a space where we just have some distance. And the thing is that once we have such kind of structure, we can kind of talk about neighborhoods or what close means in that space or what's kind of near around the point. And this is a very kind of quantitative way to talk about these things. So because we have these distances, we can take like these open balls around the point of some radius, and we can measure that very precisely numerically because of the distance. Now, a different approach to kind of studying what's kind of near a point or what's a neighborhood in a space is offered by topology, and it's much more qualitative, basically. And why do we, why we would want to do that? Well, for instance, one reason is that the notion of neighborhood might not kind of depend often about the specifics of your kind of metric, right? You might have multiple metrics, and they all give you the same kind of neighborhood structure. So that's one reason, we can kind of get rid of all those details. And another thing is that sometimes we might not have a metric, but we still want to discuss about, what's near a point, and that also implies, talking about continuity and all sorts of things. So here's just a definition of this thing that will show up often, at least in my part, and it's also kind of, I guess, at the foundation of everything that you'll hear about manifolds, although maybe it's kind of, let's say, dropped many times, or that layer is kind of hidden. So a topological space is just a set to which we kind of attach some extra structure, and that extra structure is just a collection of subsets of that set X, and we call these the open sets. And these must satisfy certain axioms. So the first axiom is very simple. The empty set and the set itself are open sets. Basically, they belong to that collection T. And another thing is that we can kind of combine these things nicely in various ways. So either by intersection or unions. That's kind of the main things you can do with sets. And then you get another open set. And here, to be precise, we are only allowed to do finite intersections, but we can do arbitrary unions. So we could arbitrary meaning like we can have like an infinite union of sets. And that's kind of like a technicality, because if you think of these things as some sort of neighborhood, if you have like these infinite intersections, you might kind of end up with nothing. So then you end up with weird things like, you have a neighborhood that's nothing, which doesn't make sense. So basically that's why we kind of restrict intersections to be finite intuitively. Okay, and here's kind of a picture. So we have some space X, and then we have some open sets here. So for instance, there's this U, there's this V, and then there's their intersection. Obviously, the whole set is also an open subset, but I haven't actually mentioned it explicitly here. And we also have the empty set that's also kind of not explicitly mentioned here. But one way to think about this is kind of splitting your space in some sort of neighborhoods, essentially. And these neighborhoods kind of offer you, so by a neighborhood, I actually mean one of these open sets. So if I have a point in one of these open sets, then that open set is a neighborhood for that point. And one intuitive way I like to think about this is kind of the resolution we look at this space, right? So it's kind of like, imagine this X is kind of like an image or something, and judging by these kind of very big open sets I've put here, it's kind of a very blurred out image. But you could imagine kind of having some very small open sets, and you look at like very fine-grained details of this space in some sense. So you could think of it like that, like choosing some resolution to look at your set. If you're more familiar with the computer science kind of side of things. Okay, so here are some examples, and it's always useful to look at some kind of finite examples so you can actually draw some things and visualize things more concretely. So these are just some examples of topologies so that we can attach to just this set 1, 2, 3. So the first one bears a special name. It's called the discrete topology. So essentially everything's an open set here. So it's kind of as fine-grained as possible, basically. So we also this kind of empty circle denotes the open set. But essentially we put like, you know, each sort of combination of sets or any subset is an open set, basically. Now, the next kind of example is another one that has a trivial name. Oh, sorry, a classical name. It's called a trivial topology. So essentially, you just have the empty set and the whole set, and that's it, right? So that's kind of the opposite of the kind of very detailed one. And then here's like the third example is just like some arbitrary example, and you can see it satisfies our axiom. So, you know, if we take intersections or whatever I've listed there as open sets, you know, you get something that's already there, and also with unions. So that's a valid one. And it's also always useful to look at something that doesn't respect the definition, and that's the last thing you see here. And this is not a topology because one is not in like an open set of its own, and it should be because it's at the intersection of those two shapes you see there. So that's one example. Now, for a continuous example, and this shows up very often, is the Euclidean topology. So basically, this is just the topology that the Euclidean metric creates. So essentially, you have all the open sets that are given in kind of the metrics space sense that you saw in the beginning. So all these kind of open balls, and you have all their unions. And that's giving you these topology induced by that metric. And more generally, this works with like kind of any metric space. So it doesn't have to be like kind of just, you know, some Euclidean space with a Euclidean metric. You could have any sort of metric on some space. You have your kind of the open balls that you can always define once you have that. And we call this topology the topology generated by the metric D. Okay, now let's kind of start to use this formalism. And I think the main thing why we care about this sort of formalism is to define things like continuity. So this is kind of the classic definition. So if you have a map between two spaces, your function f is continuous if the pre-image of any open set U in Y, so basically this thing you see on the left, that one must also be open in X. Here, if you're not familiar with the pre-image notation, this doesn't mean inverse, so you know this function doesn't have to be invertible or something, so not to be confused with that. It's just simply, let's look at where, you know, all the points that f sent to you, basically. So that's what that means. So it's the pre-image. And now this might seem kind of abstract, and I think maybe the most intuitive way to kind of arrive at this definition is, you know, if you're familiar with the kind of epsilon delta definition that you have in, you know, just regular metric spaces for continuity, you actually can show that's equivalent to something that it's exactly like this, but for metric spaces. So you have this proposition in like in metric space theory, you have, you know, if you have a function between metric spaces instead of topological spaces, but everything else is the same, then you can show that that's true starting from epsilon delta. So you could think of this, okay, let's take that result and kind of make it a definition in this context, right, where it doesn't depend on any metric or anything like that. So that's how you can, one way you could think of this intuitively. Now let's talk about some slightly more complex, in some sense, functions between spaces. So if our function is bijective and the inverse and the function itself is continuous, then we have what's called a homeomorphism. And the way to think about homeomorphism is kind of like some sort of continuous deformation of your initial space. And here's kind of a nice intuition, and it's a kind of classic joke in topology that a torus and so a donut and a mug is the same object essentially. And this kind of shows how you can deform one object into the other, and therefore they are, we say, homeomorphic. So basically there is such a function. In general, like if you can kind of visualize how you transform one space into the other, then probably they are homeomorphic. And you know, if you really put your mind at it, you can actually find a function who does that. It's a bit harder to show two things are not homeomorphic, because then you need to think, is there such a map? And you need to think of all the possible maps and stuff like that. But topologists kind of have other tricks to kind of detect such spaces by looking at what are called topological invariants. So for instance, in topology, you have holes as kind of topological invariants. So that's kind of the common thing you see between the mug and this donut. They both have that hole, and that kind of is very important. So for instance, if the other object has two holes and this one has one hole, then they would not be homeomorphic. You can show that. So that's just kind of giving an intuition for what homeomorphisms mean. And I think it's also useful to actually see an actual homeomorphism like explicitly kind of written down. But before we do that, first here's just kind of a diagram of what we want to show. So basically, this cubical surface you see here is homeomorphic to the sphere. And the way to see that is basically you imagine you just kind of compact that cubical surface into like the shape of the sphere. One way to imagine you just have some rays of light kind of emanating from the center, and basically each ray of light will kind of intersect the sphere and the cubical surface in one point, and those points will be kind of the ones we want to map, basically. And there's a very simple way to do that. So first, let's just define this cubical surface, like we know how to define the sphere, but this might be something maybe you see slightly less often. So it's just all these points, so all these 3D vectors essentially that have one coordinate is like the maximum value is 1, and the map we're kind of looking for from this cubical surface to the sphere, it just normalizes that vector, right? So if you imagine like having a vector kind of going like that, you just normalize it and you're going to get one on the sphere. So that's the main intuition. And you can show this has an inverse, which is sort of like an inverse normalization now. So we just divide the vector by the maximum coordinate, and it kind of does the sort of inverse normalization of that vector. And these you can show easily. These are continuous because they are now just kind of classic operations with continuous functions. So they're both kind of continuous functions. So this is a homeomorphism. Now there's kind of like an important corollary or observation from these kind of, let's call it proof or whatever, which is, and I think Maurice was also mentioning this, smoothness is not like a topological property. So you can't talk about smoothness of spaces or like topological spaces because these things are the same topologically speaking, right? So like these, we can all agree the sphere is much smoother than all these, kind of square, you have these corners and stuff like that. So obviously that's very non-smooth, but they are the same topologically speaking. So actually you can't talk about smoothness. And that's kind of important and will show up later. Now, something that's important is like, let's decide what sort of open sets we can associate or what sorts of topologies we can come up with. In general, we need some sort of classes of topologies that are sufficiently useful for what we want to do. And one important intuition we have about the physical space is that if we have just 2 points, we can always kind of think of them as being separate, right? They have their own neighborhoods that are disjoint or something of that kind. And some topological spaces might not have that property. So like some things could sort of be tied together in some sense because you can't find open sets to separate them. So you have to look at them together. So Felix Hausdorff came with this thing that with this property that now we say that a space is Hausdorff basically if for any 2 points, like you see here, the orange and the green point, we can find 2 open sets or like 2 neighborhoods for these points that are disjoint. So basically we can separate them. And there's a joke about this that might make you remember this definition. We say that the points can be Hausdorff. So that's one way to kind of relate Hausdorff's names with this thing. And actually I read this like in like some book, I don't know, many years ago, and I still remember it, so it actually works. Yeah, if you have troubles remembering what this means, like think about housing off some points. Yeah, there's also like this, the formal definition, it just says what I've said, but in case you want to have something that looks more formal, then that's kind of the definition. I should also say Felix Hausdorff was kind of very interesting person. He actually wrote plays and under like pseudonym, and also like philosophies, and had interesting music. So it's like a very interesting person. He also had like a very tragic kind of late years of his life, and if you're interested to read more, he had quite an interesting life. Right, now the next thing is about the basis of a topological space. So when we kind of, let's say, work with linear maps, for instance, in linear algebra, it's always useful to think about kind of having a basis for your space, and that kind of gives you a way to decompose things like linear maps. Let's see how it behaves on kind of each element of your basis. And in some sense, it's also useful in a similar way in topology to have a basis for your topology and kind of do things on these bases and then kind of generalize that to the whole space. And we're actually going to do that in one of my talks later when we talk about these things called sheaves. So yeah, what are these more precisely? So it's just a collection of open subsets of X such that we can reconstruct any open set in this topology by just taking unions from these bases, right? So basically it's like just the elementary pieces of a puzzle. We can get any other open set by just combining these basis sets. And for instance, in the case of this discrete topology that I showed you before, they're kind of singleton sets, so just 1, 2, 3. These form a basis because by just taking unions of these, we can reconstruct any of these open sets we have on the right in the discrete topology. We're going to see one more example now. So let me give you like one intuition about what kind of a Hausdorff space is in some other way. So you could think of it as a way to define what not too few open subsets mean, right? Like we don't want to have too few. Like if you have too few open subsets, you can't separate points essentially. So then you have this kind of a non-Hausdorff topological space. So you could think of it like that, right? We have sufficient neighborhoods so we can separate everything. But then a natural question to ask is, what does it mean not too many, right? Like when do we have too many open subsets? And that might be a problem if you want to do some interesting calculations or proofs or whatever, because you might have too many things to check, or things get complicated when you have too many things. So kind of coming back to our resolution kind of analogy, what's the right resolution to look at a space to do some interesting things on it? And one solution could be you can look at basically the Euclidean space that we all agree it's kind of nice to work with. So we want to preserve all that niceness, basically. So let's look at what sort of constraints we find for the Euclidean space. And what we're going to find out is that it has a countable basis. So basically, we can have these bases could be just a countable set. So basically, it's like you can find an injective function to the natural numbers, or you can literally just count 1, 2, 3, 4, all the elements you have in your basis. So you don't have something like the real numbers, that are kind of uncountably many. And to see that it has a countable basis, the way to show that is you can just look at these open balls at rational coordinates, and you pick a radius that's also rational, and the rational numbers are countable. So that's kind of the idea here. So this kind of puts some constraints in some sense of like how many open sets we can have, intuitively speaking, and we can just generalize this idea. And we say that the topological space is second countable if it admits a countable basis for its topology. So if we can find such a basis that's countable, then we are kind of good, and we don't have too many open sets. Now you might ask what happened with first countable, and that's another definition that is not going to show up, but you can show that they are related. Okay, now I'm kind of nearing the end of this, and everything was kind of building up just to these objects that you're going to see being mentioned a lot, and these are manifolds, and I think everyone has at least some intuitive understanding of what the manifold is, but the technical definition says that it is a second countable Hausdorff space. So essentially, we don't have too many open sets, but neither too few. So we kind of have just about the right amount of open sets, so we can do interesting things. That's what this says. And besides that, we can also find a neighborhood for each point. So like you see here for this point P, we find a neighborhood that's homeomorphic to some open subset of Rn's or like an open ball. So that what the second part means is that it looks kind of Euclidean, the neighborhood around P. So manifolds are essentially these things that they look locally Euclidean, and they have just about the right amount of open sets in their topology. So that's what this says informally. Now, also to kind of use this terminology that might show up, basically when you have this pair of a neighborhood and this homeomorphism you see here, that's called a chart because you're kind of picking some coordinates around that point, essentially. And this U is called a coordinate domain. So just in case this terminology shows up, just so you know what that means. And now I'm ending with this slide where I just want to kind of present what the big picture is. So on the left, we just have like a topological space, but it's not a manifold. It's not a topological manifold because it has this kind of singularity here that kind of creates trouble. So basically, that point, it doesn't look like a Euclidean space, as you can intuitively at least see. I should also mention that these are manifolds with boundary, which I haven't talked about. So you see some boundaries at the top, but ignore that for now. And so yeah, the first one is just a topological space, but then we have some slightly nicer spaces going to the right, or like much nicer actually, which are topological manifolds. So here we can find these charts I was mentioning about that makes things locally Euclidean. But as I was alluding, this is not sufficient to talk about smoothness. So if you want to, say if something's smooth or not, or kind of do calculus or stuff like that, you need some extra structure on top of this thing. And that's called an atlas, and I think Maurice will talk about that. So I'm not going to get into that, but having something with a smooth structure, like let's say the last thing you see on the right here, then it's only then we can actually start doing some geometry because we have like these tangent spaces that we can define once we have this smooth structure. And once we have these tangent spaces, we can put this inner product on tangent spaces. That's called the Riemannian metric and so on. So basically, it's only now that we can actually use geometry. And we're going to see things at all these layers this week. So basically, I'm actually going to talk in my part mostly about this first case when actually we're not in the manifold setting. So we actually can't use any geometry or like, well, Francesca's going to contradict me, but basically it's harder. Well, actually, I wanted to say it's harder to apply geometry because we don't have something that's a manifold or like doesn't have differentiable structure and things like that. But we can still do some sort of geometry, and that's an active area of research. And then you have these more things, these things with more structure where we can do calculus, and we have all this extra structure. And I think that will show up more in the part that Maurice is talking about. Okay, yeah, that's all I had to say.